Hello and welcome to the first lecture of week 9. In this lecture, I will discuss a couple of related topics which fall in the mathematical preliminaries part 2 of the course, that is Riemannian geometry, namely the geodesic deviation equation and the Riemann curvature tensor. But we did not have room to discuss them in week 8. Then in the second part of the lecture, we will include some discussion related to physics or physical laws in the presence of gravitational fields, namely the minimal coupling principle or prescription. So the references for this lecture, especially for the Riemannian geometry part, I will refer to the same text and online resources as last week. That is Nakahara's text, Carol's online lecture notes, and Hawking and Ellis. The relevant pages or sections are displayed here. And as usual, the lecture notes for this lecture will be posted on the NPTEL-NOC website. And again, as we did in last week, I will refer to O'Neill's mathematical text as a resource for those who are looking for a bit more mathematical detail or mathematical depth. All right, let's review what's on the agenda today. First, I will introduce the geodesic deviation equation, which will lead us to the fundamentally important quantity in generativity, which is the Riemann curvature tensor. And we will take the Newtonian limit of the geodesic deviation equation. Remember from last week, we had already introduced the Newtonian limit, and we will take the Newtonian limit of the geodesic deviation equation, and we will identify the components or some components of the Riemann curvature tensor with the tidal forces in Newtonian gravity. So Riemann curvature tensor represent tidal force tensor. Then I will give the formal mathematical definition of the Riemann curvature tensor and discuss some of its symmetry/anti-symmetry properties. This will help us in calculating how many independent components of the Riemann tensor are there. And we will do that for the Riemann tensor, which is derived from the Levi-Civita connection. And it will turn out to be exactly the same number as the number of components of the second derivative of the metric, which cannot be set to 0 by performing general coordinate transformations or diffeomorphisms. Finally, we will discuss some physics in the presence of gravity, in particular non-gravitational physics in the presence of gravity, and I will discuss this minimal coupling principle or prescription, which tells you how to write down the laws of physics or physical laws which govern non-gravitational phenomena if you know them already in special relativity. Okay, in the absence of gravity, if you know the laws written in special relativistic equations, the minimal coupling principle immediately gives you a way to write them down in the presence of gravity. Okay, we will learn that. And without further ado, let's introduce this geodesic deviation equation. Okay, so before that, let me just remind you what the geodesic equation was that. If you remember, geodesic equation is the equation of motion of a point particle moving in gravitational field under the influence of purely the gravitational forces, no other forces. So it's force-free motion in the gravitational field, or you can think of it as the equation for the curve of shortest distance, because the gravitation is represented by a Riemannian manifold, and in that Riemannian manifold, the equation of motion or the trajectory of a point particle is the same as that of a shortest distance curve, which is called the geodesic. Here I have the geodesic equation in blue fonts. As you can see, there are two terms. First is an acceleration term, which is proportional to the second order derivative of x with respect to some affine parameter. In this case, this is tau, the proper time. And the second term, which can be thought of as the force term in the Newtonian language, and it is proportional to the square of velocity. This gamma, which is a function of the metric and metric inverse, is called the Levi-Civita connection, which I discussed last week. Now, the strength of gravity is given by tidal forces is measured by examining whether geodesics are converging or diverging or remaining parallel. So in particular, if we don't have gravity, we expect geodesics which are remaining parallel to each other. If there's some gravitational field, then that can cause the particles to converge. For example, as you can imagine, if there's sun and if two objects are moving, they get gravitated towards the sun. So that will cause the geodesics to converge or sometimes diverge. So the geodesic equation measures gravitation via this convergence or divergence property of geodesics. So for this, consider a one parameter family of geodesics. That is, we consider a bunch of geodesics. When I say one parameter family, that means the geodesics are labeled by one parameter, which is called sigma. Okay, if I change sigma, I move from one geodesic to another. And so the continuous function of sigma, that means for the infinite domain is a one parameter family of geodesics. If I dial sigma, I go from one geodesic to the other. And these geodesics will be a function of both tau, the affine parameter along each geodesic. So tau is the affine parameter along each geodesic. And then sigma is the parameter which labels the geodesics. Okay, as I've written in the slide, sigma labels the different geodesics, and tau labels the different points on the same geodesic. All right, so we can define two fundamental quantities. First is t move, which is the tangent to a geodesic, tangent vector along a geodesic, so del x move del tau. Or in physics language, you will call it the force velocity along the geodesic. And the other quantity which measures the rate, the difference, the derivative with respect to the sigma parameter. Okay, so remember, sigma is the direction in which, if you go along sigma, you switch from one geodesic to the other. So this S mu, which measures the rate of change with respect to the sigma when you hop from one geodesic to the other, is naturally called geodesic separation or deviation vector. In particular, if you have points which are labeled by the same tau, that is on different geodesics, but points which have the same tau. For example, let me make two crosses. These 2 points have the same tau, but different values of sigma. And the distance between these 2 points, of course, distance in the sense of coordinate separation, not physical separation, not invariant distance. There's the coordinate separation. Del x move is given by this S move vector multiplied by d sigma, right? Because S mu is defined to be the rate, so then separation is S mu times d sigma. So S mu captures the geodesic separation or deviation. All right. So now x mu is a function of sigma and tau, and we know derivatives, partial derivatives commute, so it doesn't matter which order I write. So then that implies identity that del s mu del tau is equal to del tau del sigma. Okay, the rate at which the proper velocity of the force velocity is changing across sigma is same as how the separation is changing along the tau. Okay, rate of change along tau. So we can ask what is the natural candidate for a geodesic deviation, and perhaps some of you might think that this is a good candidate. Del s mu del tau, how the separation is changing as I move along the geodesic. But then, as we have seen, because of this relation, the fact that the partial derivatives commute, I can convert this quantity, the rate of change at which the separation is increasing or decreasing with tau, into the what is the different velocity with tau fixed but sigma changing. So let's say these are the velocity vectors as we go along sigma. So that doesn't really tell you whether the geodesics are converging or diverging, right? So this is not really the right quantity to look at. And in fact, as it happens in physics, most interesting quantities are second order derivatives, like acceleration. So maybe if we look at the geodesic deviation, the acceleration of that, which is given by the second derivative, okay? Second derivative of S mu with respect to tau. Okay, that is not just the rate of change, but the second order rate of change, acceleration. Now, this will not be very appropriate because if we write down this del del tau, what is this rate of change with respect to tau? This I can use chain rule to write del x mu del tau times del x mu, or del mu for short. And del x mu del tau is just the tangent vector t mu. So T mu d mu. So this acceleration, second order tau derivative of S mu, I can write each dd tau as T dot del. So T dot del acting on S mu, and then T, because it's the second derivative, T dot L of the whole thing. Okay. So this is not a frame covariant thing. Like if I compute, it might be zero in some frame, then it might, but it might be non-zero in some other frame, because partial derivatives, we know they don't transform like components of a tensor, right? So because partial derivatives don't transform like components of a tensor, they have some non-homogeneous transformation rule. They might be zero in one frame and non-zero in other frame. Then it cannot be very physical quantity. We always prefer tensors because if tensor is zero in some frame, all components of the tensor is zero in one frame. In the other frame, it has to be zero as well. So there is no ambiguity there. It's zero in some frames and non-zero in something else. That is not there. So for these reasons, this quantity, this second order time derivative of S mu is not a very good quantity to look at in general relativity. We must have something which is a tensor. And the easiest thing is to substitute this tau, the del mu's, with the covariant derivative. Okay, so if you can see, this del mu is replaced by the nabla, which is the covariant derivative. So then we know this will have a nice transformation properties. It will be acceleration, of course, geodesic separation along tau, but at the same time it will transform homogeneously under general Fourier transformation. So if it is zero in some frame, it will certainly be zero in other frames. There is no ambiguity in it. Okay, so we will go ahead with this and work out in detail what this is. Of course, the steps of algebra I will skip. You can find them in the notes because they are not that illuminating. It's mostly just algebra, high school algebra, just manipulating, adding, subtracting, and keeping track of indices. That's all it is. But I will sketch it a little bit. I'll be schematic about this. So T dot del, because we have to operate T dot L on S twice. The first time when T dot L acts on, not T dot L, T dot nabla acts on S mu, because I can use the chain rule. And if I'm using the Levi-Civita connection, which is symmetric, as most of you know, Levi-Civita connection is symmetric and the swap of the lower two indices because of torsion-free condition. So if I use the Levi-Civita connection, and if I use chain rule, I can show T dot nabla of S is same as S dot nabla of T. Okay. And then we apply a second derivative, T dot del, to this, both sides of this, and work out. It's as you can imagine, it will be a pretty long expression with a lot of indices going around, as you can see. And then you use certain identities, for example, geodesic equation. So most of you remember the geodesic equation in this form, in which all the coordinates are displayed and everything is displayed, but then there is a more cuter form which we write is T dot del T equal to 0. That is geodesic equation, and then we take because it's 0, I can take S dot del of both sides, and I can replace some of the terms here. This is a long expression. Some of the terms can be replaced using some identity, for example, the geodesic equation. And you do further simplifications, all of which you can find in the notes or on the references. You're led to something called the Geodesic deviation equation. So on the left hand side, you can see this deviation vector, and I'm measuring second order rate of change, T dot nabla squared. And the right hand side, if you go through the steps and do the simplification using some known identities, what you get is a quantity which is proportional to 2 factors of T. Just like on the left hand side, you have 2 factors of T, and then another factor which is of S, just as like in the left hand side. But there is one more factor, which is a tensor object, which is given by this. Okay, so this quantity is called the Riemann Curvature tensor. Okay, if you simplify the algebra a little bit, you will see that I can write this equation, this right-hand side, I can write in this way, the second two, it is quadratic in T and first order in S, and whatever is left over, that coefficient, I will call the Riemann Curvature tensor. So that measures geodesic separation. So the second order rate of change is proportional to this R. If these are there, both on the left hand side and on the right hand side, so don't really measure anything special. The rate at which the geodesics are converging or diverging is actually measured by the R, which is called the Riemann Curvature tensor. And in red fonts, I've indicated the formula. Okay, so to gain some intuition that indeed it represents some gravitational effect. In fact, it will represent components of the Riemann tensor will represent tidal forces. Let's take a Newtonian limit of this equation. Remember, the Newtonian limit is actually a double limit in which we first take slow speeds, that is, the particles move at the speed much less than the speed of light. And secondly, I assume that the fields are very weak, so we can take a linearized approximation. Alright, so, and then in the Newtonian limit, we also look at only the spatial components. This is S mu. So here we have S mu, and we will be only interested in the spatial components. That is what we do in the Newtonian limit, as you have seen it in the geodesic equation. Now we do the same exercise for the geodesic deviation equation. So then, for slow speeds, tau derivatives can be replaced by t derivatives, and gamma can be replaced by something linear in the metric perturbation, which will turn out to be lower order. So then, this equation, the right hand side, will also simplify. I will leave this as the homework. This people should do because I've already done the procedure for the geodesic equation. We have taken the Newtonian limit and which terms to keep and which terms to drop as an exercise. Perhaps you guys can do this for the geodesic deviation equation, how to simplify and how to keep only terms of leading order. And if you do that, you find that the left hand side, let me just point out a little bit, left hand side has two factors of t. And for low speeds, you can take t to be, as I've done for the geodesic equation, 1, 0, 0, 0. That is the particles that are almost at rest. That is the largest component. Not 1, I'm sorry. It will be c because dx will be tau. Tau will be dx dt, and x0 is c times t. So derivative of that with respect to t will give you c. Since c is much larger than all the velocity components v1, v2, v3, we can ignore them. Leading order, we can take them to be just C0, 0, 0. So, because of these two factors of T, you get the C square factor, and then S is there as usual. And because we took the 0, 0 component, we'll get to 0, 0 component of the R. Because remember, this nu and sigma, the components of T, are contracted with the components of R. So with those two factors have to be set to 0. And then we can show that this is actually antisymmetric in the swap of last two. So instead of minus, we put an extra minus sign, and instead of 0j, we will write j0. Alright, so we got this rate of change of separation, and this is given by that. Now if we compare with the tidal force equation of Newtonian gravity, which I have for your convenience here, as you can see, if I compare the S with the X, remember X is 2 points in the Newtonian gravity equation. X is the distance between a single point and another point on the same body, in fact, the center of mass. Okay, the displacement from the center of mass. So we are looking at the center of mass as one geodesic, and any other point on the extended object as the other geodesic. Okay, and their separation is xi. Okay, so if I replace si by xi, then we can identify c squared times the Riemann tensor of these components with this tidal force. Okay, so this is what I meant. So this Riemann tensor, what we mathematicians call Riemann tensor, turn out in physical language, they're nothing but the components of the tidal forces. So this is what I've written in the blue fonts in the slide. The tidal force is the Newtonian limit of certain components of the Riemann curvature tensor. Alright, so now we have a nice physical motivation to study the Riemann curvature tensor. Now math and give the formal definition. Let's go back to Riemannian geometry. So the Riemann tensor, by definition, the tensor is a multilinear map. By now, you must have got accustomed to the definition of a tensor. All of them are multilinear maps. So this is a multilinear map which takes three vector fields. So this chi of M represents the space of vector fields, and it consumes three vector fields and spits out one vector field. Okay, so then it must be a rank 1, 3 vector tensor, right? If it had spit out a scalar R instead, then it would have been a rank 0, 3 vector, 0, 3 tensor. This is how tensors are defined. So in this case, as I mentioned, because they eat up three vector fields and spit out one vector field, so the rank 1, 3 tensor. How does the action work? So let's feed R three vector fields, x, y, z are three vector fields, and the resulting object will be another vector field which is given by this. Okay. These nablas are, of course, most of you know covariant differentiation. Covariant differentiation with respect to x, if you want to write in some basis, it will be x mu, nabla with the mu, whatever it acts on. Okay, so these have all meaning, and hopefully by this week, you know how to operate with covariant derivatives that were already done in the last week. So this Riemann tensor is defined for affinely connected spaces, okay? Because you need to know how the covariant differentiation works, and we all know that to specify covariant differentiation, you need to specify the some connection. In GR, we'll always be interested in Levitch-Guethe connection, not any random connection. But R in general is defined for affinely connected spaces. All right, so now let's write the components of R. So let's supply X to be some basis element E hat rho, Y to be another basis element E sigma rho, E sigma hat, I'm sorry, and Z to be E nu hat. Okay, so then you get this quantity, and of course, because it maps three vectors into another vector, the resulting will be another vector quantity which has a basis element and a component. So this component I've written this way so that it remembers that you got it by feeding this R, rho, sigma, and in that particular order. Actually, so the order is slightly different. This is what I wanted to point out. I'm using Nakahara's convention. Not every author uses this convention. I think Carroll uses slightly different convention. So be very, very careful when you're reading multiple books. Always first check what is the defining equation for Riemann tensor to know the convention they're following. In general relativity, there is no unanimity in the convention for defining Riemann tensor, and there are broadly two camps. And I belong to the camp in which if you feed this rho sigma nu in that order, then the Riemann components will have rho sigma at the last and nu at the last. And this mu, because when you feed R three vectors, it spits out a vector. That's why this guy on the right hand side, you have to put a vector basis element. Okay. And then in purple font, I've done the computation, so you can use this formula here. And I've also used the third term is missing because we already know for coordinate basis element there, the Lie bracket of E mu with E rho with E sigma will vanish because they're coordinate basis elements that we have done while discussing Lie brackets. So the third term is not there. We only need to compute the first two terms. And if you compute, you get this form of the Riemann tensor. And now you can see that this is exactly what we had when we wrote down the Geodesic deviation. All right. Okay, so this is a very important physical quantity because it poses tidal forces. The presence of gravitation is given by the Riemann tensor component having non-zero value. If it has zero value, which it can, it will be, that means that at that point space is there's no gravitation, and we can show that this is Minkowski. If it is zero everywhere, then the solution has to be Minkowski space. Okay, so this is the tensor, and we already know if we are in a Riemannian manifold, we have a metric, so I can use that metric to lower this upper index more. I've lowered it using the metric. Okay, so this is what is more commonly used in physics. Riemann tensor with all four indices lowered. When I defined it with three lower indices and one upper indices. It was a rank 1,3 tensor. But now, if we are in a Riemannian manifold, I can use the metric to lower it and convert it into a rank 0,4 tensor. They both contain the same information, so as far as physical information is concerned, it's no different. Okay, now let's look at some of the properties of the Riemann tensor. So, naively speaking, Riemann tensor, you might think that it has four indices. So, and let's say we are in d-dimensional space-time. So, we are in a manifold which has big d dimensions, and let's say we have a metric G. So for this kind of a space-time, you might think the Riemann tensor will have number of components d to the fourth, because there are four indices: mu, nu, rho, and sigma. Each of them can take d different values. So then total number of values which R can take, because each index can take d different values, will be d times d times d times d, which is d raised to the fourth, which is a very intimidating number. Let's say if you put even d equals 2, let's say in one space and one time in 2 dimensions, this number is staggeringly large. 2 to the 4 is 16 components, and if you go to our world, which is in 4 dimensions, 4 raised to the 4 is a huge staggering number. But it will turn out that the Riemann tensor has many symmetry properties. As a result, some components get related to the other, and the number of independent components actually lesser. So let's see what those symmetry properties are. The first thing I would say is that the Riemann tensor, either the upper or the lower, it is antisymmetric under the swap of the last two indices. Here you can see rho sigma, and I put a minus sign, and sigma rho. So whenever rho sigma, the last two indices are switched, and their order is switched. From rho sigma, we went to sigma rho. Then actually there's a typo here, it should be a minus. Okay, so then it is antisymmetric under the swap of the last two indices. And this is true by definition, because remember the last two indices here, as you can see, the last two indices determine the order of the differentiation. So they are defined with a minus sign. So if I swap rho with sigma, it will get sigma times rho, which is minus of this. So this negative sign comes because by definition, we have this antisymmetry. If we swap x with y, this is antisymmetric. All of the terms, as you can see, even the D bracket is antisymmetric in the order in which x and y appear. So this is true in general, antisymmetric in the last two indices. And then there is something called the first Bianchi identity, which is given in this by this equation in the purple fonts. As you can see, the mu upper index is not changing, it is same. What is changing is the order in which the lower three indices, nu, rho, sigma, are appearing. In the second term, I have done a cyclic permutation, so of nu, rho, sigma. So rho comes first, sigma is second, and then nu last. And in the third term, we do a further cyclic permutation in which this rho is sent to the end, and then sigma becomes the first one, and nu the second one, and rho the third. So you can say that it is nu rho sigma plus cyclic permutations of cyclic terms of nu rho sigma. And there are only going to be two terms, because three objects you can cyclically permute to get three combinations. So where does this come from? So it turns out this only holds if you have a torsion-free connection. So this is not true in general. If you are using some connection which is not torsion-free, that curvature, which is derived from a non-torsion-free connection, will not satisfy the first Bianchi identity. Okay, The idea of this Bianchi identity is closely related to something called the Jacobi identity. Most of you have taken some class in vector spaces and perhaps know this. Jacobi identity for covariant differentiation looks something like this. You have this Lie bracket of Delmo, sorry, not Lie bracket, this is a commutator bracket. So this commutator bracket is just, you operate on whatever is to the right in different order. So mu, this commutator is del mu will act last, del mu will act first, and whatever it is to the right hand side, minus del mu will act last, and then del mu will get to act first on whatever is there on the right hand side. Okay, so the commutator, and if you take three such, if you have a repeated commutator, you can show when you expand the commutators, all of them cancel among each other and give you 2. So the Jacobi identity which I've written is trivially true, because the left hand side, when you expand, open up the commutators and write in terms of triple three derivatives, they will all cancel each other out among each other, and you'll get both sides answer. However, when you compute this using rules of covariant differentiation, this first term, for example, you can show that that is given by this Riemann tensor, some term involving the Riemann tensor and first derivative of phi, and then a second term which is proportional to the torsion tensor times the second order derivative of phi, and then finally a third term which is again derivative of torsion tensor with phi. So if the torsion tensor vanishes, these two terms will drop out, and each of these terms will be given in terms of the Riemann tensor times some derivative. And you can show that being 0 means the Bianchi identity, implies the Bianchi identity. So to be technical, this is only called the first Bianchi identity. There is a second Bianchi identity. We will discuss a bit later. And then the third symmetric property or anti-symmetric property is that Riemann tensor is anti-symmetric under swap of the first two indices. Okay. So here, for mu nu, I went to nu mu in the right hand side, and as a result, I picked up a sign. Okay. Now this also holds not for a general connection, but for metric compatible connection. That is, connection for which the metric is covariantly constant. Remember, metric compatible condition is something like del mu of G equals 0. Okay. Only for metric compatible connection. How do you show this? Oh, well, you need to use the identity that if I take the commutator bracket of this covariant derivative acting on G, the unique component of that, unique component of the whole thing, then you can evaluate this by using the rules of covariant differentiation, which I've covered in the past week. Then you get this combination of the Riemann tensor, two terms which are the Riemann tensor with the first two indices swapped, mu, but the last two indices remain as they are, plus a term or minus a term which is proportional to the torsion tensor times the derivative of the covariant derivative of the metric. Now, if the connection is metric compatible, this term will go to 0 because del acting on G gives you 0. This term also goes to 0 because the covariant derivative acting on G will go to 0, will kill it. Then you have sum of these two equal to 0, which gives you this anti-symmetric problem, desired anti-symmetric problem. Okay. So if you have a metric compatible connection, if you are deriving your Riemann curvature from a metric compatible connection, then the Riemann curvature would be symmetric under swap of the first two indices. And the last one is something which is called the pairwise symmetry, and it holds for connection which is Levitch-Vita, that is both metric compatible and torsion free. Okay. Here, if you look at the indices, what I've done, I hope it is not, I hope it is visible to everybody. What I have done, I will write it here, maybe it's more visible. I have the first pair of indices, and I'm going to swap it with the second pair. Rho sigma, this is equal to rho sigma first and mu nu second. Okay, so it is symmetric. they are the same thing. So this is called the pairwise symmetry, and it holds for the Levi-Civita. Maybe I will leave it as a homework, or assign it as a homework, or give it as a problem in the whole final exam, But please try to prove this, that the Levi-Civita connection will lead to Riemann curvature, which has this pairwise symmetry property. Okay. So now that we know about all the symmetry properties of the Riemann curvature, in particular, we will assume Levi-Civita, so we'll get maximum amount of symmetry or antisymmetric properties. We want to count how many independent components are there if we get the curvature derived from a Levi-Civita connection. So it will turn out that the four identities of four symmetry and antisymmetry properties determine that the number of independent components is not d raised to the 4, but d squared times d squared minus 1 over 12. Okay. How do we see this? We can do the math a little bit. So indeed, we started with d raised to the 4. Maybe I have it here. Yes, the argument is there. So instead of using 4 indices, use these uppercase Latin indices, r sub ab, which is mu nu rho sigma, in which big A, this uppercase Latin index, all represents this mu nu, and this uppercase Latin index B represents rho sigma. Okay, so r sub uppercase A and uppercase B is equal to this. It's a condensed notation. Instead of using 4 indices, I'm using 2 indices, where each uppercase Latin index represents 2 Greek indices. Okay, so then each of these uppercase Latin indices, which represent 2 Greek indices, they can take d choose 2 values, because mu and nu take d different values, but they have to be distinct because of the antisymmetry and the swap of first 2 and swap of last 2. So mu and nu must take distinct values, and rho and sigma must take distinct values, but they can take they have to take distinct values out of a d possible number of values. So d choose 2. Number of different combinations A can take is then number of different combinations of 2 distinct indices from d possibilities. So that is d choose 2, and same for B. Okay. So A and B, this is what I have on the slides. A and B can each take n, which is d choose 2 values if they are antisymmetric. But we also have the pairwise symmetry. So R of AB is equal to R of BA. That is same as the pairwise symmetry of the Riemann curvature tensor. So we can think of this as a 2x2 matrix which has pairwise symmetry, which has this exchange symmetry. In that case, if A and B can take n different value, the symmetric object will take number of independent values or components will be, as we know, for a symmetric matrix, n times n plus 1 over 2, which is this. N is d choose 2, and if you write down n in terms of d, you get this figure. But this is not all. We also have the Bianchi identity, right? So Bianchi identity will give you d choose 4 constraints. Why is that? Well, Bianchi identity for this, if you take any 2 components, you can write it with the lower index as well. If you take any of the 2 indices to be the same, you can check yourself, and I will leave it as a homework, that if you choose mu and nu, or mu and rho, or something else, any 2 components, any 2 indices to be the same value, then you get 0 equal to 0. So the things cancel out on the left hand side and give you 0 equal to 0. You don't generate a constraint. 0 equal to 0 is not a constraint. So in order to get a something non-trivial, left hand side non-trivial, non-zero, you must take mu, nu, rho, sigma to be all distinct. They must be all distinct. Now we have each can take d possible values, and if we want to take 4 of them to be distinct, we must take, then the number of equations which will result from this is d choose 4. So the Bianchi constraints, Bianchi identity constraint gives you d choose 4 constraint. So this many we had after using the symmetry of the indices and as well as the pairwise symmetry. And then we also got to subtract the number of Bianchi constraint, which is b equals 4, and then you end up with this figure of b squared times, again a typo, b squared minus 1 over 12. Now, if you remember the class in which we went to a falling frame and we were able to set the metric at a point to Minkowski and the connection to 0, but we were not able to set all of the second order component of g to 0. And the number of second order derivatives of g which could not be set to 0, it was also exactly the same as the number of components of the Riemann tensor. So the Riemann tensor actually measures the failure to go to a freely falling frame and still make the Minkowski, that is, kill gravity altogether. If going to a freely falling frame was to eliminate gravity entirely, which is what Einstein at some point believed, that if you go to a freely falling frame, then it is same as moving in some space which is without gravity. Okay, the gravity and acceleration will cancel each other, and you will get to Minkowski space or gravity B. But that is not true because tidal forces cannot be eliminated. So even if you go to a freely falling frame, there will be some component in the second derivative G which cannot be set to 0. Okay, that means tidal forces cannot be eliminated by going to a freely falling frame. Alright, so I hope that impresses upon you the utility or the importance of Riemann curvature tensor. It is central importance. This, in fact, Riemann tensor equal to 0 means you're in flat space. Riemann tensor non-zero means there are no tidal forces, so gravity. You're in a space with gravity.